So we have now understood what is the concept of this Macaulay duration and how to define the Macaulay duration and what it says. Now let us understand it more clearly using say numerical example to compute the Macaulay duration. Okay, so let us consider this example. Calculate the Macaulay duration of a 4-year annual coupon bond with 6% coupon and a yield to maturity of 5.5%. So, we have understood that the face value of this bond is 100. Okay? So, the present value of cash flow therefore can be calculated using the present value formula here we have just seen in the previous slide with the interest rate that is 5.5%, that is 0.055, right? So while computing this you have just let us now understand this table more clearly. You will understand the Macaulay duration. Okay, so we have 4th year and the coupon is actually and the annual coupon, so we'll have 1 2 3 4 period. Okay, and CT is just the FR. Okay, that is or simply the interest amount what you want. So like 6% from 100 is therefore 6 rupees or $6. Okay, which is here it can be clearly understood. So first year you are getting this coupon amount of $6. Second year you are getting the coupon amount of $6. Third year you are getting the coupon amount of $6, and then the fourth year you are getting your final payment. That means 6 rupees or $6 plus the 100 initial payment. Okay, or initial investment. So that is why it is the 106. Okay, now so using this formula here you can easily compute the the present value of CT. Okay, for example, for the first period it will be easy. So I will just show you here. You will be able to follow this. Okay, so this become CT. This is 6 multiplied by 1 plus I, that is 0.055 to the power 1. Okay, and which will give us 5.6872. Okay, and for the second year, okay, the present PVCT will therefore be equal to 6 multiplied by 1 plus I. Okay, also 1 plus 0.5 1 plus 0.055. So we will have, okay, like 1.055 to the power minus 2, and then we will get the value this one. Okay, similarly we'll just place I is equal to 0.055 here and TT is equal to this 3 here. Okay, and CT is equal to 6. Okay, you will get this value, right? And therefore, okay, in the same way, right, CT is equal to 106, and then we will have 1 plus 0.055, okay, to the power minus 4 will be this one. Okay, and therefore the total here, right, this one is what? This one is the price of the bond, right? So this is the price of the bond, which is the denominator in our example, in our formula here. Okay, and therefore weight should be, okay, this value, okay, this value divided by this value, okay, which will give you this one, right? So 5.6872 divided by 101.7526 will be 0.0559, right? In the same way, so you can simply calculate this value as 5.3907 divided by 101.7526, which will be 0.0530. Okay, similarly you can compute the WT for third year and fourth year, and the sum should be equal to 1. Okay, if we add this, then it will be equal to 1, right? Now you have got WT and you have also T. Okay, so in the formula it says like the Macaulay duration is simply the sum of T multiplied by WT, and therefore we can have like T multiplied by WT. So 1 multiplied by WT here is equal to 0.0559. Okay, and 2 multiplied by 0.0530 is equal to 0.1060. Okay, all the figures are actually rounded it up. Okay, and therefore you will get this figure. So now if we add this, we will have 3.6761, which is nothing but your Macaulay duration, right? So this value is the Macaulay duration, okay, or simply called D, right? That is what I have written it here. So the price of the bond is the sum of present value of all cash flow P, okay, which is this one. This is exactly this one I have written, okay, and the weight is simply PVCT divided by P, okay, and therefore WT you are going to get it, okay. So the Macaulay duration is the sum of the last column here, okay, which is simply 3.6761. So what we have noticed here is this Macaulay value, okay, or the DMAC here, or the duration is actually less than the term to maturity. So what is the term to maturity in our case here? N is equal to 4, but we have found that the DMAC is equal to 3.67, right? So this value is actually less than the 4. Okay, so Macaulay duration of the bond is less than its time to maturity of 4 years. Okay, so approximately, therefore, we have like it take around 3.6 years. Okay, now consider another example. Okay, and we will be clear what is Macaulay duration, right? So this example again says that calculate the Macaulay duration of 2 year, okay, semi-annual coupon bond with 4% coupon per annum and a yield to maturity of 4.8% compounded semi-annually. Okay, we will also consider here also this bond of the face value is equal to 100. Okay, and therefore we can compute the cash flow of the bond, okay, that occurs at, okay, every half year. Okay, so we will have 1, 2, 3, and 4 half years. Okay, so we'll only have 2 year, and it is a semi-annual coupon bond, and therefore, okay, every year there are 2 times this, like coupon you are paying the coupon, and therefore we will have 1, 2, 3, 4 half years. Okay, now the present value of the cash flow can be calculated using the formula what we have just understood. Okay, with the I is equal to now this 4.8 divided by 2, which will be 0.024, okay, or 2.4%, right? So with this we will get this table using the same way what we have understood in the previous slide. So we also have again like one half year, second half year, third half year, and fourth half year, and the coupon amount is 2%. Okay, so here like 4% divided by 2, so we'll have 2%, that is 2. Okay, and we will get first year and first half year, second half year, third half year, and this is the fourth half year cash flow. Okay, and the present value of cash flow or present value of the coupon payment what you have here is, okay, using the I is equal to 0.024, we will get the value. This is for first half year, this is for second half year, third half year, and fourth half year, and add this to get the price of the bond. Okay, so the price of the bond is the sum of this third column here, okay, which will be 98.491 cents. So here remember that this price is less than the face value, so this must be a discount. bond, right? Okay, so now what is the weight here? Weight is simply this 1.953 divided by 98.491 will be 0.0198. Okay, similarly we will have the weight for second half year period is 1.907 divided by 98.491, which will be equal to 0.0194. Okay, similarly we will get the value for or the weight for the third half year and fourth half year. Again you will see that the sum should be equal to 1. Okay, and now once you get this, we will now multiply this WT with the T, that is the number of half year you have. So 1 multiplied by 0.0198 will be the same 0.0198. So 2 multiplied by 0.0194 is equal to 0.0388. Okay, 3 multiplied by 0.0189 is equal to 0.0568, and 4 multiplied by 3.7676 is, sorry, 4 multiplied by 0.9419 is equal to 3.7676. Okay, so we'll add this here, right? We will get 3.88. Once again you can see here that, okay, so the duration or the Macaulay duration is less than the total period. Okay, that is 4 half year, so 3.8. So actually, to understand this problem here, so we will have the Macaulay duration of this bond can be computed as simply 3.88 divided by 2, which will be 1.941 year. So I believe now you have understood how to compute the Macaulay duration. Okay, if the coupon payment is for annual coupon or if it is for semi-annual coupon. Now, okay, consider this quick question, okay, and think a little bit and try to answer by your own. Okay, Right. So an investor buys a 6% annual coupon payment, okay, bond with 3 year to maturity. The bond has a yield to maturity of 8.5% and is currently priced at 980 per 1000 of par value. Okay, so the bond's Macaulay duration therefore can be computed. Okay, and you need to compute the Macaulay duration. So use the formula the way we have just developed and try to answer this question. Okay, take 2 minutes time right now and do this by your own. Okay, so now you can just compare your answer with this answer. So the Macaulay duration D can be computed as this. Okay, so for the first payment period, we will have 60 divided by 1.085 multiplied by 1. Okay, plus the for the second one, we will have 60 divided by 1.085 to the power 2, or simply we will call square, multiplied by 2, plus this is the third payment period. So we will have 1060 divided by 1.08 to the 1.085 to the power 3 multiplied by 3 whole divided by the price here 980. So that is here, and therefore we will have 55.2995 rounded it up to 4 decimal point. Okay, plus 101.9346 plus 2489.6477, okay, divided by 980, which you will get 2.70. Okay, so if you have got this value, then you have understood the Macaulay duration computation, right? Now Again, notice that this value is actually less than what is the 3. Okay, what is n? So Macaulay duration always less than the term to maturity. Okay, and therefore they are not equal, right? Okay, so far in the Macaulay duration formula, it was assumed that the cash flows were at a regular interval. Now, what if the cash flow is not in a regular interval, or if it is actually irregular? Then the formula will be modified, right? So we can extend the formula for when the cash flow occurs at irregular interval. In such case, I will be the rate of interest per base period, for example, per year, and the discount factor, that is 1 plus I to the power t, will be applied in the model. Okay, and therefore the Macaulay duration will then be expressed in terms of the number of base period. Okay, to understand this, let us consider a bond having the following characteristic, that is face value of f, coupon rate r, time to maturity n, okay, and the rate of interest I is the yield to maturity per coupon payment period, and ct, which is equal to fr for t is equal to 1 to up to n minus 1, and cn is basically fr plus the f. Okay, with this characteristic we will now have the Macaulay duration as d is equal to 1 upon p times sum of tfr divided by 1 plus I to the power t plus nf divided by 1 plus I to the power n. Okay, which is equal to 1 upon p. Okay, take this fr out here and we will rewrite that fr sum of the present value of t, that is simply, okay, we will write the way we have computed the present value for ct is now computed for t. Okay, so simply then we will write pvt for t upon 1 plus I to the power t. Okay, now here the nth n, and now this one is actually v to the power n. Okay, so we know here that the price of the bond is simply, okay, fr a angle n at I plus f v to the power n, assuming that this f is the redemption value. Okay, f is the face value which is equal to the redemption value, and therefore the equation, remember I have written it in many ways, right? I have used sometime m, sometimes c. Okay, and now I'm using here at, so don't confuse here. So this is actually the like face value which is assumed to be equal to the redemption, or the redemption value assumed to be equal to the face value. Okay, then we can rewrite this formula as d is equal to fr, okay, fr sum of pvt plus f of n v to the power n whole divided by, okay, p. Okay, fr a angle n at I plus f of v to the power n, or simply we will have this fr and fr. Okay, or simply we will have like the face value and face value. Take this face value out here, we will have face value. Okay, f, and then this f here out, and then we will have f divided by f is equal to 1, and therefore we are not writing it here. Okay, so we simply have like r I a angle n at I plus n v to the power n divided by r a angle n at I plus v to the power n. Remember what is this I a? This is the increasing annuity formula. Okay, that exactly here the sum of present value of t. Okay, sum of present value of t is nothing but the increasing annuity. Okay, on the present value of increasing annuity, okay, given n year and high interest rate. So now we will rewrite this formula as d is equal to ria angle n, okay, plus nb to the power n whole divided by r a angle n plus b to the power n. Okay. So let us understand what is modified duration. The modified duration is actually the refinement portion of the Macaulay duration which adjusts the yield to maturity. Okay. So the modified duration is actually tells us the price sensitiveness of the bond with respect to the change in the interest rate. And therefore we can simply take this as the rate of change of the price, okay, with respect to the rate of change of the interest rate. Okay, so it is basically the first derivative of the price. So we now have the first derivative, the dp by di. Okay, and knowing that there is a there is an inverse relationship between the bond price and the yield. Okay, the first derivative should be negative, right? So dp by di is negative, and therefore we will consider the percentage change in the price per unit change in the rate of interest, that is minus of dp by di time 1 upon p. Okay, so now using the formula we have derived earlier, okay, that is p is equal to sum of the present value of cash flow, which is equal to sum of Ct divided by 1 plus I to the power t. Okay. Now we can rewrite the formula as minus 1 upon p dp by di, which is equal to minus 1 upon p. Okay. And the derivative of this term with respect to I, or we can simply have like d by di of summation of Ct upon 1 plus I to the power t. Okay. Now we can solve for it, and in the right hand side equation, therefore here will be minus of 1 upon p summation of minus t times ct divided by 1 plus I to the power t plus 1. Okay. Now we can have this 1 plus I, okay, to the power t multiplied by 1 plus I to the power 1. Okay, and then take this 1 plus I to the power 1 here in, like write with it p, so that I have just taken it here. Okay, so 1 upon p time 1 plus I summation of tct divided by 1 plus I to the power t, right? So this equation is simply this earlier equation writing in a different way. Okay, now so we have understood that this is basically the present value of the present value of p time t, right? So present value of ct, right? This one is present value of ct time t. Okay, and therefore you can simply have 1 upon 1 plus I summation of t time present value of ct divided by p. Okay, this one, this term is, we have just derived it as Macaulay duration. Okay, so the Macaulay duration was this. Okay, summation of t time wt. So we have taken this term as wt in the Macaulay duration. Okay, so this can therefore be written as dmac divided by 1 plus I. Okay, or we can define the modified duration as d modified, which is equal to dmac divided by 1 plus I, or simply we will write d by 1 plus I. Okay, what is this then? So this is simply, okay, the modified version of whatever the Macaulay duration we have understood. Okay, so consider this example to understand the modified duration. Calculate the modified duration of the first example we have just understood, that is a 4-year annual coupon bond with 6% coupon and yield to maturity of 5.5%. Then we can use the modified duration formula as the Macaulay duration divided by 1 plus I, and we will get the answer that we have already calculated the Macaulay duration for our first example. We have understood it like 3.6761, just remember, okay, and therefore the modified duration in our case here is simply this value, that is 3.6761 divided by 1 plus I, which is equal to, okay, that is 3.484, okay, or the modified duration is equal to 3.6761 whole divided by 1.055 will give us a value 3.484 years. Again, we will see that this value is less than the n. Okay, that is fourth year. So what does this mean? What does this mean? This means that the bond drops in value by 3.484%, okay, per 1% or 1 percentage point in increase in the interest rate. Okay, please try to understand this statement that, okay, whenever you will get the value of modified duration as like this 3.484, this means that the bond, because there is an inverse relationship between the bond price and the yield, and increase in the like interest rate will actually reduce the bond price, okay, and therefore the bond price drops in value by 3.484% per 1 percentage point increase in the interest rate, okay, and not simply the 1% increase in the interest rate. We will call it as 1 percentage point increase in the interest rate. Okay, so I think now you have understood how to compute the Macaulay duration and how to compute the modified duration. So in the next session, we are going to learn the duration with the price correction, and then we will introduce the convexity concept. Okay, so in the next session, we are going to learn the convexity. See you in the next session.